Welcome to part 3 of my Kinetics series. In part 1, we talked about the basics of rates, getting rates from concentration time graphs and the initial rates method. In part 2, we talked about orders, working them out, and an example from data, the shapes of the rate concentration graphs of the different orders, and the overall order of a reaction. Now in part 3, we're about to talk about the rate constant K, how to figure out the units of K, how to calculate K, the temperature effects on K, and the Arrhenius equation. Let's start with part 3. So how do we calculate K? Well, that's actually quite straightforward. So we had an example from part 2 with a reaction that involved hydrogen and nitrogen monoxide going off to form water and nitrogen gas. And the rate equation happened to be this. Rate equals K, concentration of H2, which was first order, hence it would just be a 1 up there, which we leave blank, times by nitrogen monoxide, which was second order, so it's squared. All we do to work out K is we just rearrange. So we divide through by the hydrogen and the nitrogen monoxide squared to form this. Simple maths that you would have done at GCSE or earlier when you were quite young, just dividing through, but it's just algebraically instead this time. And all we do then is we just put in the values. So for example, if rate was 2 moles per dm cubed per second, hydrogen was 1, and so was nitrogen, it would be 1 times 1 squared. That would equal 2 over 1. Therefore, the value of K would equal 2. And we can, it's just plugging in values, which you'll most likely get given in data or asked to work out earlier on in questions, but most likely just given data. It's simply just rearrange a nice small equation and plug the numbers in. It doesn't get much more difficult than that. Now, units. Units are the bits that are a little bit more tricky. Still quite straightforward if you're mathematically minded, and if you're not, don't worry, I'm going to show you exactly how to do it. Now, the units of K, when we have a rate equation like the one before, rate equals K H2 NO second order, we have to remember units. So concentration, represented by these square brackets, are moles per dm cubed. Now rate, the units of rate, moles per dm cubed, second to the minus 1, which I showed you why it was that in part 1 of this video series. Now, if you remember, we just rearranged to get K. We've got rate over H2, concentration of NO squared. And all it is then is we just put the units in. Instead of the numbers that you were given, all we do is put the units in. So that's the same as rate, so moles per dm cubed, seconds to the minus 1, times by mole per dm cubed, which was hydrogen, times by moles per dm cubed. However, this time, because it's second order, I've got to put a squared in there. Simple as that. And what actually happens then, again, same as algebra at school, well, moles per dm cubed here cancels out with moles per dm cubed up here, and you're left with seconds to the minus 1 divided by moles per dm cubed squared, which when we rearrange that comes out as dm to the 6 moles to the minus 2 seconds to the minus 1. If you remember, when we bring something that's under a fraction to the top, we put a negative sign on the power, and we just change the sign. So if it's got a negative, it will go to a positive instead. So moles per dm cubed squared, all of that squared, is mole squared dm to the minus 6. And because it was just over, we just bring it to the top. And just to be mathematically more correct, I've just put the positive power at the front before the two negative powers. So that bit at the bottom there, just this term here, is equal to mole squared dm to the minus 6. And like I said, we'll just change the sign on the powers to bring it to the top. As simple as that, and that's how you work out the units for this particular example. If you had a different situation where you had, they were both first order, for example, then we wouldn't have the squared in there, and it would just be dm to the 3, mole to the minus 1, second to the minus 1. All we're just looking at the units. It's just simple maths. You would have done it algebraically using x's and y's and things like that. Instead, we're just using moles per dm cubed and applying that simple maths. Like I said, each situation is different, so it depends on the order of your reactants and how many reactants you got. You could have a rate equation with 10 different reactants and they all have a different order. That's going to be more complicated. Or you could just simply have rate equals k of h squared. Therefore, k would just equal seconds to the minus 1, because it would be rate, moles per dm cubed, seconds to the minus 1, divided by one lot of concentration. So the moles per dm cubed and the moles per dm cubed would cancel out. Therefore, it would be k would be seconds to the minus 1. That would be the units. So that's how you work out units. Now, how does k and temperature relate? Well, it's just one small simple fact here, and you'll just have to memorize this, but it would make sense when I explain it. So k doubles for every 10 degrees C, approximately, that is. So k doubles for roughly every 10 degrees C increase in temperature. Well, the reason for that may make sense. If you look at reaction, as you put up the temperature, the rate increases as temperature increases. Well, if we look at the rate equation, rate equals k and then a concentration of a reactant with some order. Well, the concentration doesn't change when you heat something up, so that variable stays constant. So the only other variable that can change is k. So k must increase to get the rate to increase. Because if we say this value was 1 and the rate was 1, therefore at that time k is 1, so 1 times 1 is 1. If the rate was now suddenly 2, that stays constant at 1. Well, k is now going to have to equal 2. So 2 equals 2 times 1, and here 1 equals 1 times 1. It's just simple things like that. It makes sense when you're looking at it from that mathematical aspect. Now, if you relate this to chemistry, why does an increase in temperature make the rate go up? That's because of simple collision theory. If you have particles zooming around that need to hit into each other, if they're travelling really slowly towards each other, they take a long time before they'll collide to react. As you have ones with a lot of kinetic energy, because as you know, when thermal energy goes in, it makes particles speed up and they zoom everywhere. Well, they're suddenly flying and whacking into each other. The reaction is going to happen a lot quicker. They can hit each other quicker, find each other quicker, and also there's a larger amount of molecules or particles with the required activation energy. So they're going to hit into each other and the reactant's going to be used up, more products are made quicker. So that's collision theory in a nutshell, and that's why temperature increases, because they're more likely to collide and have a successful reaction. Now let's look at the Arrhenius equation. So the Arrhenius equation links in with k. So k equals a e exponential to the minus ea over rt. So that's the Arrhenius equation. So as you can see, k is the rate constant, which we've just been talking about. A is a pre-exponential factor. Effectively, you can just treat it as a constant number depending on the reaction you're looking at. Ea is known as the activation energy, which you may have come across from Boltzmann's distributions and things like that. R is a gas constant, which will be given to you most likely in data, or if you're at home you can research it online. And T is temperature, which in this case we're looking in the Kelvin rather than Celsius or Fahrenheit. Now what we can do is this, we can actually work out Ea and the activation energy and the pre-exponential factor if we plot it on a graph. Now we can work out K if we're given rate and the concentration of the reactants, we can work out K. And if we know the temperature that a reaction was taken, the data was taken at, we also know T. Well, from K here and T here, we can actually plot a graph and we can work out EA and A. Now, to get it to a way that we can plot a graph, you may be looking at it and thinking, how do I plot that on a graph? It takes a bit of maths. Now, there's two ways you can do this. You can either follow through the maths with me, if you're mathematically minded, or when I go through it, feel free to skip, say 30 seconds or so, may take a bit longer, and just look at the answer and see how to plot the graph and memorize how to do that. But if you're mathematically minded, it makes a lot of sense and it's quite simple maths. If you're doing A-level, it's something that you'll do quite a lot. And this is why A-level maths helps with chemistry. Now the derivation of this starts with the equation. So k equals a exponential to the minus ea over rt. So the first thing you do is use the natural logarithm ln. Well, when you do ln of e, that basically just cancels out and makes 1. So what we can do is we can ln, as I like to say it, ln each side and put it into there. And there's another law of logs that if you have a log, ln, or for example, it could also be log to the base 10 or something like that, similar situation of, say, a times by b, that is the same as saying ln a plus ln b. That's just a mathematical concept that you need to know if you're doing A-level maths, and you may have come across it already. So what we can then do is we can say ln k equals ln a plus ln e to the minus ea over rt. And if you remember here where I said ln e is the same as 1, meaning we can rewrite ln k equals ln a minus ea over rt, because the ln and the e have just cancelled out, so it brings the power down. So if we say e to the x equals 1 times by x, is a better way of putting it, e to the power of x. So when we do that, we can rearrange it to be ln k equals ln a minus ea, activation energy, over the gas constant r, times by 1 over t. I've just taken t out because it shows what I'm about to say is it's a straight line graph and it shows this a bit easier. And that's just the same as having a t in the bottom there. It's just the same as having a t there, like it was on the equation above. So when we look at this, you may think, might look a bit familiar, or when I point it out, you'll definitely notice that it looks a bit familiar. Y equals c minus mx. But y equals mx plus c, except for I've just rearranged it to y equals c minus mx, because the gradient is a minus. Well, because we've got that, like I said, we can plot this if we know k. So we know the y values, which are k, well, ln k in this case, which ln is just a mathematical function that you can use on your calculator. So we now know the y values. And t, if we know the temperature that these were taken at, we now know the x values as well. So we can just plot a graph out of this. So when you plot a graph of ln k versus 1 over t, I'll just write the finalised equation at the top here again. So ln k equals ln a minus ea over r times by 1 over t. So they're your x values, they're your y values, and because it's in a certain way, a bit like y equals mx plus c, well, c is the y-intercept. Well, we can look here. So that's the value of c. In this case, value of c is ln a. So the intercept here is ln a. It's nice and easy, just like anything you would have done at lower level maths, except for using y equals mx plus c, and there's just a lot more letters here. Here, the gradient, which you can work out from the values, you can do dy by dx, the change in the y divided by the change in the x, equals minus ea over r. And r is a constant, r is a value that you know. So for example, if we said the gradient was minus 1 in this example, so minus 1 equals minus ea over r, which would be something like 8.314. That's equivalent of ea equaling 8.314. And it's nice and simple like that. As you see, we go from something that you're thinking, how on earth do I plot that? A quick bit of maths, and we have a nice graph here that we can use. We can plot ln k against 1 over temperature, and we can find out ln a from the y-intercept, and we can learn the activation energy of the reaction from the gradient of that line, as it's a straight line plot. If we didn't do all this learn business and all this maths, we would have had an exponential graph that could look something like this, and we could never get a gradient of that, and it would be really hard to figure out what the values are. But this just makes it a lot more simple. That's the end of part 3, and that's the end of the whole series of kinetics. Please share this with your friends if they're struggling with a similar topic. Please like and subscribe for more videos. Thank you.